Hello, this is Mengze. Welcome to the presentation of our paper, Assisted Counterexample-Guided Inductive Optimization for Robot Path Planning. The presentation is divided into following 5 parts: background knowledge, objectives, ACGL-based path planning algorithm, experimental evaluation, conclusion, and fieldwork. So let's start with some background knowledge. Let me introduce how CGL and optimization technique works. Starting with define decision variable x and cost function fx, we define the constraints with assumed derivative, which is x in bounds, fx new smaller than fx current. Fx current is a current cost function value, and fx new is a smaller cost function value we would like to generate. Then we define the property with assert derivative, fx new larger than fx current, and we pass them to the verification tool. If the verification fails, which means a smaller cost function value is found, so we update x and fx current with fx new. Then we go back to start another iteration to find smaller cost function values. And if the verification succeeds, we need to check if the precision p reaches the upper bound. If it didn't, so we need to update the p and go back to start another iteration. If it reaches the upper bound, so we need to end with the current result. Path planning can be considered as an optimization problem, so CGL can be applied to achieve the optimal path by iteratively requesting counterexamples from SAD or SMD solvers. Here is an example of applying CGL algorithm to solve a path planning problem. The aim is to figure out a path which has shortest distance from starting point S to target point T, avoiding all obstacles. After first iteration, the blue path is generated by CGL, and a green path with smaller cost function value, which means with shorter distance, is generated after the second iteration. So, optimal paths can be generated after massive iterations. However, CGL-based path planning algorithm requires large execution time, and requesting counterexamples from SAD or SMD solvers is the most time-consuming process. So in order to improve the efficiency, we propose a novel path planning algorithm based on ACGL. ACGL combines CGL with an accelerate algorithm, which relies on CGL to preserve the optimization ability, and relies on the selected accelerate algorithm to improve the efficiency. So in this work, gradient descent is selected. Here is an example explaining why ACGL is more efficient than CGL. Assume we have a cost function fx, so on the left is updated by CGL. Starting from the initial position, it updates optimal candidate only by requesting counterexamples. And as for ACGL, starting from the initial position with requesting counterexample once, then gradient descent is applied until it traps in a local minima. So at this moment, counterexample is employed again to generate a smaller cost function value, and the gradient descent is applied to update the optimal candidate till the global minimum. The optimization process of employing ACGL contains fewer times of requesting counterexamples, and the gradient descent, which is much faster, is applied instead. This is why ACGL is more efficient than CGL. Next, let me introduce objectives. We have 3 objectives. Firstly, develop an ACGL algorithm with gradient descent as an accelerate algorithm to generate optimal paths. Secondly, evaluate the proposed ACGL-based path planning algorithm. Thirdly, compare the results with other traditional optimization techniques-based path planning algorithm. Overall, the main object of this work is to propose and evaluate a novel offline mobile robot path planning algorithm based on assisted counterexample-guided inductive optimization algorithm. In order to achieve ACGL-based path planning algorithm, there are 2 steps of applying ACGL to path planning problems. Step 1. Formulate the path planning problem as an optimization problem. Define decision variables, cost function, and set constraints. Step 2. Apply ACGL to find an optimal path that minimizes a cost function and satisfies the constraints. Let's start with path planning problem formulation. Path planning is to find the valid optimal path from a starting position to the desired position that avoids all possible obstacles in the motion space. The optimal path consists of a sequence of points consecutively and sequentially connected by strict segments. Here is an example. We can define a starting position S as P1 and the target position T as Pn, and define the points consisting of the path as L, which contains P1, P2 to Pn, and the cost function can be defined as this. The cost function JL is the length of the path, and N is the number of points on the desired path. Then we define the obstacles and the environment limits. So the optimization problem for path planning can be written as this. To minimize the cost function JL, wherever points on the path is within the environment limits, but cannot be within the obstacles. Before applying ACGL to path planning problem, let's go review the CGL-based path planning algorithm. In CGL-based path planning algorithm, directive assume is used for modeling the constraint set, like obstacles and the environment limits. Also, assume is used to set a constraint GLI smaller than GLI minus 1, which means the new generated cost function value must be smaller than the current cost function value. And the directive set is used for holding a global optimization condition, which is GLI larger than GLI minus 1, so we need to verify the satisfiability of G optimal. Then, if the verification fails, which means a smaller cost function value is found, optimal candidate GL is updated if a smaller cost function value is generated from a counterexample. And variable P is used to control the precision and discretizes the state space. Starting with number of points n equals to 1 and precision variable p equals to 1, after maximum time of iterations, optimal paths can be generated. Now let me introduce ACGL-based path planning algorithm. It is quite similar to the CGL-based path planning algorithm, but it takes an additional input, that is gradient descent function GL. ACGL additionally employs gradient descent to calculate optimal candidates iteratively. Similar to CGL-based path planning algorithm, we use a assume directive to define GLI smaller than GLI minus 1, and we use a set directive to define the optimization condition. And it requires counterexamples once. If smaller cost function value is generated, we pass them to the gradient descent function. Gradient descent function is employed to update the optimal candidates. So new optimal candidates are generated either by extracting from counterexamples or by applying gradient descent. This is how ACGL-based path planning algorithm works. Now let's move on to the experimental evaluation. There are 3 experimental goals. First one is effectiveness, to evaluate the effectiveness of the ACGL-based path planning algorithm. And the second one is efficiency, to compare with CGL-based path planning algorithm. And the third one is to compare with other state-of-the-art approaches. So in this work, PSO-based path planning algorithm and GA-based path planning algorithm is selected. And here is the experimental setup. Tools for executing CGL-based path planning algorithm and ACGL-based path planning algorithm are as follows. ESBMC is selected as a model tracker, and Bolector is selected as a SMT solver. And as for executing JA-based path planning algorithm and PSO-based path planning algorithm, MATLAB is selected. As for the experimental environment settings, motion space is modeled as square, obstacles are modeled as blue circles, safety margin is represented by red circles. Here are 2 experimental environment settings. The first one, the setting 1, it has 1 obstacle, and as for setting 2, it has 4 obstacles. Point S is the starting point and the point T is the target point. So the aim is to generate the valid optimal path from S to T, avoiding all obstacles. In order to answer the first 2 experimental goals, which is efficiency and effectiveness, we need to evaluate CGL-based path planning algorithm and ACGL-based path planning algorithm in setting 1 and setting 2. So set the maximum execution time to 2 days. Here are the results. Red passes are generated by a CGL-based path planning algorithm, and the blue dotted paths are generated by a CGL-based path planning algorithm. As we can see, a CGL-based path planning algorithm can generate passes extremely close to the global optimal paths and solve the optimal path planning problem. So the first experimental goal, effectiveness, is achieved. In order to identify the second experimental goal, efficiency, we need to compare CGL-based path planning algorithm with a CGL-based path planning algorithm. So we plot the reduction trend of the cost function values for setting 1 and setting 2. The horizontal axis represents the times of optimizing the path planning problem, and the cost function values are shown in the vertical axis. As we can see, the blue line represents the ACGL-based path planning algorithm, and the red line represents the CGL-based path planning algorithm. For both setting 1 and setting 2, the blue line is below the red line, which means with the same execution time, the ACGL-based path planning algorithm can always generate a smaller cost function values if compared to CGL-based path planning algorithm. So a CGL-based path planning algorithm generates passes closer to the global optimality with less execution time. So the second experimental goal, efficiency, is achieved. In order to identify the experimental goal 3, comparing with other state-of-the-art approaches, so GA-based path planning algorithm and PSO-based path planning algorithm are selected. Firstly, let me introduce experimental results of applying GA-based path planning algorithm in both setting 1 and setting 2. Here, for each environment setting, it contains 3 n equals to 4 cases, and 3 n equals to 5 cases, and 3 n equal to 6 cases. The execution speed of using GA for solving the path planning problem is extremely fast. Each experiment was completed in a few minutes. However, as we can see, the passes generated by GA-based path planning algorithm are further from the global optimality if compared to the passes which are generated by ACGL-based path planning algorithm. And there is uncertainty that the cost function value converges differently, and sometimes even fail to converge to a global optimality. So if compared to GA-based path planning algorithm, ACGL-based path planning algorithm is more stable and reliable. Then, as for evaluating PSO-based path planning algorithm in both setting 1 and setting 2, here are the results. For each setting, it has 2 kinds of results. Passes generated by the algorithm with appropriate parameters, and the passes generated by the algorithm with inappropriate parameters. And for both appropriate parameters and the inappropriate parameters, we got a n equals to 4 case, and the n equals to 6 case, and the n equals to 10 case. With appropriate parameters, like number of particles, acceleration coefficients, neighborhood size are set to the appropriate values, we can get the passes which are really close to the global optimality. So the cost function value always converges to the global optimality if the parameters are set to the appropriate values. So PSO-based path planning algorithm with appropriate parameter is fast, stable, and reliable. Here is the overall results to answer experimental goal 3. GA-based path planning algorithm is faster, while ACGL-based path planning algorithm is more effective and more stable. PSO-based path planning algorithm is stable, fast, and reliable, but not easy to tune the parameters. However, ACGL-based path planning algorithm is much easier to tune. And here is a conclusion and future work. We presented a novel mobile robot path planning algorithm, which relies on the ACGL algorithm to solve the optimal path planning problem. And the proposed algorithm can generate optimal passes with significantly shorter execution time than the original CGL-based path planning algorithm. And compared to other state-of-the-art algorithm, it is slow, but it is stable, reliable, and more robust. And as for the future work, develop other accelerate algorithms to assist CGL and explore the best accelerate algorithm for CGL to solve the optimal path planning problems. That's basically everything about our paper. Thanks for listening.